Okay, wait, I can explain. I accidentally squared myself. Well, that's the joke. I mean, I'm squared, but it wasn't accidental. I wrote a lot of code. There's an equation somewhere on the screen right now. I don't know how to point at anything, but I've taken the pixel locations and squared them. No time to explain now. I need to unsquare myself, and very gradually I'll reduce that power until, there you are, I'm back to normal. I lied again. I'm now square rooting myself. So that's the worst sentence I've ever said. Up until now, I've been always using the original pixels from every frame and then moving them. Instead, I'm going to iterate. So I'm going to repeatedly do that. I've moved them. I'm going to move them again. I'm going to repeat that again and again and again and again. Look at me now, I'm a fractal. I'm the Mandelbrot set. But I'm not. That was a pun on the Mandelbrot set. Wonderful fractal. Hugely overrated. It's the golden ratio of fractals. Forget it, we're gonna get away from that. There are much better fractals out there, and I was one of them. I was a Julia set, but I was the boring one, the one right in the middle. Instead, this time, square root myself, duplicate, but before we do it again, slide to the left. Or the right, your left. I forget which way I did it in the code. Slide somewhere, do it again. Slide, do it again. Repeat, 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 repeat. Look at me now. It's Julia set, Matt, check that out. Here's a fun game, follow the mug. Where is it now? Could be anywhere. I apologize for making you see this. We'll talk about fractals in a moment, but first we have to deal with the coordinates of where a pixel is in a video frame. It's measured from the top left corner. Ridiculous. I'm gonna put a point on the screen in a moment. I don't know where, because I'll run the code to put this in afterwards. Okay, so I was gonna mark a point on the screen. Did I say where? Doesn't matter. Put it anywhere. I assume I put it carefully in the top left corner over here.
Oh, of course.
So once you've got a point with its coordinates, I can convert that into a more useful coordinate system. And if you're thinking, well, Matt, you're just gonna move the origin to the center of the frame. No, I mean, yes, I'm gonna do that, but I'm also gonna turn them into a complex coordinate. Well, a complex number scaled so the height of the frame is equal to 2. And complex numbers, they're so great. You don't need to know about them for the purposes of this video, but the point is you can manipulate them like normal numbers. So every coordinate in the frame has kind of just got one number instead of 2. And if we square them, they move in an unusual way in the 2D space that is this frame. So here's a bunch of points. I square them. Look at them go. So what it means is my code can take every single pixel in this frame, take its coordinates, turn them into a complex number, square that complex number, see where that corresponds to as a new location, and then move the pixel from the original place to the new place. And that's how we go from this to this. To get a sense of complex squaring, we can move complex number z around, and you can see its square, z squared over here, move around correspondingly. And as you move z around, you get all sorts of crazy behavior. Now, on the real number line, that reverts to just regular square numbers. So if I cross 2, 2 squared is 4. That makes sense. But everywhere else, sometimes, like, look at this. As I go around the unit circle, z squared's getting away. It's all the way back over there. I have to do another lap with regular z to catch back up again. Now, I don't want to go too much into the nuances here, but whenever z crosses the unit circle, watch this. Z squared crosses at exactly the same time. Look at that. So anywhere out here, z squared's further away from the origin than z is. But right when you cross here, they're exactly the same distance. And that doesn't matter. Like, we can be wildly apart, opposite sides, and still when I come in this way they cross simultaneously. And then inside, doesn't matter where z is, z squared's always closer to the origin. So inside the unit circle, squaring gets you towards 0, and if you were to repeat this, square and square and square and square and square, you'd end up right in the middle. And then outside, if you square, it gets further away and further away and further away. That's all you really need to know about squaring complex numbers. So how does this become the Mandelbrot set? Well, the Mandelbrot set is basically a game of complex number sumo wrestling, where the point has to stay inside the circle despite being repeatedly squared. Although, as we already saw, if you're already inside the circle and you keep getting squared, you just go to the middle. If you step outside though, then you fall away. But what's going to make you step outside? Well, your opponent? is plus c. That is a constant, which is also a complex number. So every time you're squared, you get bumped by plus c, and then squared, and then bumped, and then squared, and then bumped. The game now is, can you stay inside the circle? And whether or not you're successful entirely depends on what that plus c is. So in this game, one wrestler is at the origin, which we're going to have as a complex number, and here comes their opponent. Plus c equals 0.35 plus 0.21 I. Now, the very first move, when plus c comes into the ring, because squaring 0 does nothing, the first thing that will happen is a shove in the plus c direction, which is why we're now at 0.35, 0.21. We square that result, we add on plus c again, we move to a new location. Now, I'm not going to animate them moving every single time we update the position, so if we click through, you can see after a while the point, well, it just stays inside the circle. So in this case, plus c loses. The other wrestler wins. Time for a new game with a new plus c opponent, and actually this time, plus c will win. The point will get pushed far, far away from the arena. And I have cheated slightly by referring to the arena as a circle. It's actually a more complicated shape. And that's the shape we're working towards. It's the Mandelbrot set. It's all the points such that the game goes one way or the other. And my mate Ben Sparks did a number 5 video about this a while ago. In it, he has a phenomenal GeoGebra file. And I asked him very nicely if he could show it to us.
Thanks, Matt. The basic idea, as you know, is pretty simple. If you start at the origin and square that number, you get 0. Less interesting perhaps than you expected, but if you add a constant, then you'll get that constant, and then if you keep doing it, that constant, you square it and add the constant again, you'll get that point. If you square that point and add the constant, you'll get that point, and if you keep going, you'll follow this nice spirally path in this case. Obviously, it depends which constant you add each time, and that's why I can drag the C around and you see the different paths start happening. So we get a tighter spiral, or we get different sort of spirals over here, depending on what C you use in iteration. But sometimes it's unstable. It doesn't come back stable, unstable. And that's what these splodges in the background are doing. Black for stable, blue for unstable, where you've kind of pushed it out of the arena. And we can just find out which is which. So I'm just colouring in the screen. I'm actually going to try and see if I can find the boundary between stable and unstable, the black and the blue, by working my way around. And I mean, if I can go slowly, you can see the spirals inside and the unstable bits outside, but I really want to find out where they change. Look at that! We're getting a nice little visualization of a shape which I think is familiar to a lot of mathematicians, or at least it is now. But imagine being the first person to see this shape. And if I turn on the picture you get with high resolution, this is the Mandelbrot set. The points inside are stable and the points outside are unstable. Stable, unstable, stable, unstable, stable, unstable. Nice.
And that's the Mandelbrot set. It's called a set because it's the set of all the values of C such that you lose or win the complex sumo game. It depends slightly on how you define things, and to explain that, Future Matt is going to write some more code to visualize it. I'm not going to do that. My code is so slow, this would take forever. Instead, check this out. This is a very low resolution Mandelbrot set, but there's a slider at the top there. This is just for dramatic reveal. So as we reduce the grid size, we get a better and better resolution Mandelbrot set. And I'm going to refer to this as the Mandelbrot set. I use the word set a lot. Technically, it's just the perimeter, but I'm saying set to mean all of the inside. If you're wondering where the colors come from, they're technically artificial. You can add colors as a measure of how fast does the game end? Like, how fast can you get to the middle, or how fast can you get thrown out of the complex sumo ring? So whenever you see colors on one of these fractals, whoever's made it has put them on there. In this case, it's my friend Christian Lawson Perfect, who coded this up such that it responds as I move that slider around. It's actually recalculating it each time. Incredible. So if that's the Mandelbrot set, what are Julia sets? Well, they're the same thing, just more interesting. The Mandelbrot set assumes you start at the origin at value 0, then you play the game. A Julia set is exactly the same idea, but you can start anywhere you want on the complex plane. So your player starts at some complex value, then you play complex sumo, see if you end up in or out of the circle eventually. So this is the trivial Julia set. This is all the places where you can start and safely remain within the circle when you're adding a C value of 0. And I can change the C value, thanks to Christian's incredible coding, by just moving the mouse around. So wherever the mouse is, that's the new starting C value, and all the points you can see on the screen are the places where if you start there, you'll stay within the circle forever. And I occasionally mix these up when I'm saying them, because the Mandelbrot set are all the C values for the one starting central point, as opposed to the Julia set, which is a fixed C value showing you all the starting points, but you get the idea. Now for some C values, you can see all the starting points that are safe and you'll win the game are in one big connected, albeit fractally, region. But for other C values, like out here, look, they become these disconnected, like fractal dust. Like, oh, I love the ones here, like the spiral effects. Look at that, isn't that phenomenal? Look, it kind of merges in the middle. Actually, if I zoom in a bit, okay, I'm going to see if I can get that middle bit so we watch it join. So the two ends come in, scoop around. Oh, look at that. Isn't that phenomenal? I could spend hours exploring this. And you can too, because we'll link it in the description below. And if you find any fun ones, as you can see in the bottom left-hand corner, you can read off what C value you're looking at, and you can then share those, so put them in the comments below, and other people, you can just type them in, and it will take you straight there. Ah, Julia sets, they're incredible. Exploring by moving the mouse around is a lot of fun, but what if we want to see a couple of different Julia sets at once and categorize them in a sensible way? Well, we could plot the pictures according to what their starting value of Z is. So we have the boring one at 0, 0. We could then add on the starting positions +1 and -1. We see how they compare. We could add in +I and -I, that works as well. And we can do the corners. So you've got 1 + I, -1 + I, and so on. We could push that by going out to 2 in each direction. We could increase how many we can see at once by, let's say, we do the half values, or maybe more values. In fact, we can do loads, and if we want, we can change the grid size to fit more in at once. Yes, it's me again in the future, messing with Christian's phenomenal code. I'm going to make the grid size smaller and smaller so we see more and more of them at once. We've still got the boring circle in the middle, but look at all these other interesting ones coming in. And if you make them incredibly small, it's the Mandelbrot set. Oh, come on. It's true, the limit of plotting Julia sets according to their C values is indeed the Mandelbrot set. But the Mandelbrot set, of course, was just a plot of C values. And it kind of makes sense, because if you're starting at the origin and you're adding C, your first move puts you to where that Julia set is. So the Mandelbrot sets, it's not all the Julia sets, but basically, you know what, let's increase the samples per grid, make it a bit bigger. Let's actually fade across a bit. And this is actually the image I was showing you before. The Julia sets are just the Mandelbrot set that we're trying to get away from. I'm so angry, I could square myself. In fact, I've squared myself. Now, if these fractals are all about squaring a complex number, why, when I fractaled myself on camera at the beginning of the video, still very sorry about that, did I use a square root? Why was I going in the other direction? Well, I was literally playing the game of complex sumo in reverse, because to win the game, to be in the set, you have to stay inside the unit circle. So what if you just look at all the points in the unit circle and then play the game backwards to see where you could have been the move before, or the move before that, or the move before that, and still ultimately end up in the circle? That's what I was doing. This is what it looks like if you just apply it to a circle. This video was partly inspired by a Matt Henderson tweet from 2020 that I saw, where they've got this phenomenal animation showing basically that effect. And I was like, well, I want to do that, but I want to apply it to video footage. So I sat down and wrote my own code, which is why it's terrible. Could I have used off-the-shelf software? Yes! Humankind have put a phenomenal amount of effort into this stuff, because that's how we do visual effects and all sorts of fantastic post-production on video. I was doing it so inefficiently. I mean, there are shaders and all sorts of things you can use, and that's how Christian Lawson Perfect was able to make such a great interactive Julia set explorer. Highly recommend you check that out. But I wanted to do it myself. I wanted to get into the maths because I enjoy it. much like the sponsor of this video, Jane Street. They use mathematics to solve complex problems in the financial world, and the reason I love them as a sponsor is they don't want your money. You can't give them money. They don't want it. They want to they want you to either apply for a job or look into their fantastic programs.
And this time I'd like to mention, in addition to their exciting maths and programming and trading roles, they do employ people in other fields which you may not have considered. The infrastructure teams form the backbone of Jane Street, keeping the day-to-day operations of the firm running seamlessly. They handle things like all the legal and compliance matters. They deal with the taxes and the finances, which are non-trivial. They manage their offices, the human resources. They help direct their creative projects. They're the ones I'm involved with. Now, they are hiring people for all of those teams in their offices in Hong Kong, London, New York, and Singapore. Now, I visited these offices. They are amazing spaces. I mean, this is why I work with Jane Street, because I get to visit their offices. They've been designed with people in mind, and between you and me, very mathsy people in mind. So if you're interested in finding out more, do check out the link in the description below and look at all their departments, the many, many opportunities you could have to work at Jane Street.
That's it. Do check out the fractal description, and huge thanks to Jane Street for sponsoring this as well as many other of my videos. The video's over, but I'm still here because there's one more cool thing that Christian made for me that I wanted to share with you. Before I moved the mouse around the Julia set itself to change the C value, Christian did a second one where I moved the mouse around the Mandelbrot set, and that changes the C value of the Julia set you can see on the right over there. And that means you can see how the C value for each Julia set corresponds to where it is in the Mandelbrot set. And if I stay inside the Mandelbrot, the Julia set is connected. If I go outside Mandelbrot, it's now infinitely many disconnected fractal bits of dust. And as I get closer, you can see, it's coming back together. And the moment I step back inside, even this ridiculous bit of the fractal set, it's connected again. But because it's one of the ridiculous bits, it's like a crazy connected. It's so great. If you want to see more about this, I've been meaning to make this video for a very long time. 5 or 6 videos, another video came out covering similar topics, and I thought, well, I won't bother doing my video now, but it's been several years since that came out. I'll link to it below. More great things about the link between Julia sets and the Mandelbrot set, and if you want to play with this as well, I will link to it below. It's just so cool. Like I say, I really could spend ages exploring all of this. That's actually the end of the video. Thank you so much for watching. And a reminder, I'm going to the Edinburgh Festival Fringe, doing all 23 or whatever shows. Come and say hi. I'll sign your calculator afterwards. And then I'm on tour around the UK. A few people have asked, because they've seen on some but not all, we're trying to get this on all of them, an upgrade to VIP, which is a bit of a misnamed type of ticket, but the upgrade means you're allowed to show up early, come in, watch the sound check when I'm setting up the stage. I'll do a Q&A, chat with you, answer your questions, and you get some exclusive merch, and I'll do the kind of meet and greet for you before the show. So I'll sign calculators, take selfies, all of that. So if you're someone who wants to see the sound check and wants to leave straight after the show, you can do that. Buy the normal ticket, come along to the show, say hi afterwards. I look forward to seeing you all there. Hopefully we'll announce more dates soon. And finally, I'd like to apologize for starting the video with Squared Matt. That's a jump scare, is such a haunting, just he's behind me, isn't he?
Hi.
Oh, wait. I just thought I'd join the end of the video.
Why would you do that?
I want to say like and subscribe.
No, you're horrifying.
Oh my goodness, haunting. I'm sorry, well I gotta go appear in the dreams of some math students anyway.
Good.
I'm sorry.